This lesson is on explaining graphing rational functions. To do this, we're going to be locating holes and asymptotes. The first thing is to factor both the numerator and the denominator if possible. In this example, they already are factored, and what I'd like you to notice is that this expression is not in lowest terms. In order to get it in lowest terms, you're going to have to cancel the x with the x. However, the domain of this function is such that x cannot be equal to 0. And by canceling it out, we actually have a related function, but one that actually can have x equal to 0. This is where we have a hole. So our hole is going to be at x equals 0. And if you use a graphing calculator and then go to your table, one of the things you're going to notice is that right here, it will say in your table that when x is equal to 0, y is NaN. Now, NaN simply means not a number, and that's our hole. When you graph this, you actually put an open circle where that hole occurs. Next, we're going to move on to finding vertical asymptotes using that reduced equation. We've already canceled the hole. To do this, what you're going to do is set the denominator equal to 0. And when you set x squared plus 1 equal to 0, you get x squared equals negative 1, and then x equals plus or minus I. Therefore, we really don't have any vertical asymptotes, because what we would be doing is we'd be looking for a positive or negative real number that x would be equal to. If it's equal to an imaginary, it simply means you do not have an asymptote. So now we're going to go on to locating the horizontal asymptotes. To locate the horizontal asymptotes, what you do is you determine the degree of both the numerator and the denominator. The degree of the numerator is 1, and the degree of the denominator is 2. When the degree of the numerator is less than the degree of the denominator, the horizontal asymptote, which I'll abbreviate as HA, is y is equal to 0. So now what we'll do is we're going to look at our graph and see that everything we just did actually happens. Remember when we crossed out the x value, I said that there was a hole. So right here at x equals 0, even though it looks like it's continuous, right exactly at 0, you have to put in an open circle, and that's your hole, indicating your hole. Your graphing calculator will not do that for you. That's something you're going to have to do. Again, we stated that there were going to be no vertical asymptotes, and as you look at this graph, you can see no verticals, and there is a horizontal at y equals 0. So y is equals 0 is the x-axis, and right there you can see that the graph is approaching but never actually hitting. In our next example, we again factor the numerator and denominator to see if anything cancels. The numerator, however, in this example does not factor. However, the denominator does factor. Therefore, there's no holes. To locate the vertical asymptotes, we're going to take a look at the factorization of the denominator. So we're going to factor this, and as you can see, it does factor as 3x plus 1 times x minus 2. So what you're going to do at this point is you're going to set 3x plus 1 equals 0, and that becomes x is equal to negative 1/3, and you're going to set x minus 2 equal to 0, and that'll give you x equals 2. X equals negative 1/3 and x equals 2 are your vertical asymptotes. Now let's look at the horizontal asymptotes. Since the degree of the numerator is 2, and the degree of the denominator is also 2, whenever you see the degree of the numerator equal to the degree of the denominator, what you're going to do is you're going to take, let me do this in red so you can see it. What you're going to do is you're going to take the leading coefficient 6 over the leading coefficient 3, and that means that y is equal to 6 over 3, or y is equal to 2. And that's your horizontal asymptote. So now let's take a look at our graph and see how close our estimation was to what we're seeing. And if you remember, we have no holes. We do have 2 vertical asymptotes. One of the vertical asymptotes is at x equals -1/3, which, let me do this one in blue, would be right about here. A little difficult to draw. And there's another one at x equals 2, which is right here. And as you can see, our graph is getting closer and closer to that vertical asymptote, but it never actually touches it. And the last thing is we said that we had a horizontal asymptote at y equals 2. And here's our y is equal to 2. And as you can see, this portion right down here is getting closer and closer. But if you could go out with your graphing calculator, changing your window, and try and go as far as you can to the right, you'll see that it never actually touches. And we have one last example of graphing rational expressions. In this example, the numerator does not factor, and so therefore there's nothing to cancel, and so again, there are no holes. On to the vertical asymptotes. Again, what you're going to do is you're going to take the denominator x minus 5, set it equal to 0, and then x equals 5 is going to be your vertical asymptote. Now on to the horizontal asymptote. Again, what we're going to do is we're going to look at the degree of the numerator, 2, and the degree of the denominator, 1. And since 2 is greater than 1, what this indicates is there are no horizontal asymptotes. However, there is an oblique asymptote. Finding the oblique asymptote requires a little bit of work. What you're going to be doing is you're going to be dividing using long division the denominator into the numerator. And so right here you are going to be going x minus 5 into 2x squared plus 14x plus 7. X goes into 2x squared 2x times. And then 2x minus 5 is negative 10x. 2x times x is 2x squared. Then you're going to subtract. Subtract means change your sign. So that minus is going to become a plus, and we end up with 24x, and then you bring down the 7. You then take x, divide it into 24x, it goes in 24 times, and then again you 24 times negative 5, which is negative 120, and then 24 times x, which is 24x. Again, you're going to subtract, and you end up with a remainder of negative 113. This quotient right here, 2x plus 24, tells us what our oblique asymptote is. Y is equal to 2x plus 24. And you'll recognize that as the equation of a straight line where the slope is 2 and the y-intercept is 24. So last of all, let's again take a look at our graph and see whether it matches everything we just said. What I've done here is I've graphed in red the equation that we were actually looking at, and then I graphed the oblique asymptotes so you could compare it in blue. And as you can see, this red graph, is coming very, very close, but it's not actually touching this blue graph. So that is our oblique asymptote. We also said that there was a vertical asymptote at 5, and so right here at 5, again you can see that our curve is getting closer and closer to that, but it's not actually touching it. So these are the 3 cases of graphing rational functions. We did look at holes, we looked at vertical asymptotes, we looked at horizontal asymptotes, and the horizontal asymptotes had 3 situations. One where the degree of the numerator was less than the degree of the denominator. Then we looked at when the degree of the numerator equaled the degree of the denominator. And then finally, in this last case, which had the oblique asymptote, the degree of the numerator was greater than the degree of the denominator by 1.